But this is what you're going to be seeing in this course, okay? Oh yeah, I guess I have all that in here. So when we plot a titration curve, we are going to be plotting pH on our y-axis and volume of titrant on the x-axis. And we are going to talk about what titrant means versus titrand. And I'll show you that in the next slide here, 1 or 2 slides. Okay. And you're going to get depending on the type of titration, you're going to get a curve that's going to look somewhat like this. Right. That would be for the titration of a strong acid titrated with a strong base, so adding small amounts of strong base. And so let's go on. So that's just sort of in general. So you might see a setup like this. You probably do this in lab, where we have a flask that contains the titrand. So this is what we are titrating. In this case, we're going to say we're going to titrate a strong acid. And we're going to add to it, from a burette, the titrant, the strong base. So we are titrating a strong acid with a strong base. So that's how we would say that. So the titrant, the strong acid goes in the flask, and we're adding small amounts of base until we get to an equivalence point or an end point. Equivalence point and end point aren't exactly the same term. We'll probably use them somewhat interchangeably in this class. Equivalence point refers to a stoichiometric equivalent of acid and base at a particular point. But endpoint is a point you observe typically with an indicator. So like if we're doing a titration of a strong acid and we're adding base, if you use a phenolphthalein indicator, which is I think maybe what you'll do in lab, you're going to see a color change from colorless to pink. And once you get to that point, that's the end point. It is not exactly the equivalence point, but it's very, very, very close. Just a slight terminology difference. Okay, so we're titrating a strong acid with a strong base. And so what we're going to do is think about how the pH is changing in the flask. Okay, the burette's going to contain the strong base. Its pH doesn't change. We're adding that base in small amounts to the flask. The pH of the flask, the solution in the flask, is going to change. So if we have a strong acid, our pH is going to start out low, acidic. The pH won't change very much until we get to the equivalence point, at which point we're going to see a very sharp rise in pH. And then beyond that, there will be a flattening out of the curve when the pH is dominated by excess base. So an equivalence point would be sort of at the middle of this vertical part of the graph. Okay? So by I, it's somewhere halfway between where this really starts to change pH and where it starts to flatten out. Okay? There are more mathematical ways of figuring out exactly the volume of the equivalence point, but you don't need to worry about that. Well, you will, but not in the graphical way. Okay? Does that make sense? Okay. So again, we're exploiting this reaction. Strong acid plus base, neutralization to form water. Okay? So I like to think of the titration curve as having 4 different points. Okay. And the first point is before any titrant has been added. And in this case, we're saying that our titrant is the strong base. And the strong acid is the titrand, that ends in D. We'll just typically say titrant, and then not worry about the word titrand. Okay, so before any titrant has been added, that's our sort of point 1. Okay. Well, before any base has been added, in this case specifically. So what is the pH going to be dependent on in the flask? The amount of acid in the flask, right? So the pH is dependent on the amount or concentration of acid, strong acid, H3O plus or H plus, however you want to write it, in the flask. Okay? In that solution in the flask, if we're titrating HCl, we're going to have both H plus and Cl minus present in solution, right? And we know that Cl minus doesn't affect the pH. So we're going to essentially ignore that. The next point along our titration curve, point 2, is somewhere between our starting pH and the equivalence point. Point 3 is going to be the equivalence point. Okay? So we're somewhere between there. So that means some amount of hydroxide has been added. But not enough to reach the equivalence point. Okay? So fewer moles of OH minus have been added than there are H plus in that original solution. So we'll do moles of OH minus are less than moles of H plus before reaction. Okay? Once they react, we have no H minus left over. That's why I'm specifically saying before reaction. So as we add that hydroxide, it's going to react with the H plus, right, in this reaction. Okay? So that reaction occurs to completion. H plus plus OH minus occurs to completion. So if we have fewer moles of OH minus than H plus, we're only going to have H plus after those react, plus the other spectator ions. Does that make sense? We'll do an example, but be thinking about that, okay? So, in point 2, the pH again is dependent on the amount of H3O plus. So point 3 is the equivalence point. By definition, the equivalence point says that the moles of OH minus added is equal to the moles of H plus originally in the flask. So if we start out with 0.1 moles of H plus in the flask, at the equivalence point we've added 0.1 moles of OH minus. Completely react, we're left with 0 moles of H plus and 0 moles of OH minus, according to this reaction. So what will the pH be? 7, presuming we're at 25 degrees Celsius. Okay? The nice thing about strong acid, strong base titrations, assuming we're at 25 degrees Celsius, is that the pH at the equivalence point is always 7 at 25 C. That's not going to be true for weak acids titrated with a strong base or weak bases titrated with a strong acid. Then point 4 is anywhere past the equivalence point. Doesn't have to be at the top of that curve. Okay, or if it takes 15 milliliters of sodium hydroxide to get to the equivalence point, at 15.01 milliliters, we're at the region beyond the equivalence point, and all of these things that I'm going to say next are true. So, the pH at this point is dependent on excess hydroxide. Okay. All of our hydroxide that we've hydroxide has completely reacted with H3O plus. There's no H3O plus in solution. Once we're past that equivalence point, we keep adding OH minus. That species is going to dominate the pH. So pH is going to be dependent on hydroxide concentration. Okay? Make sense? Okay. So let's work through an example. Now, because of the 4 regions that we've defined, it's really useful to know the volume at which the equivalence point occurs. If you know that, then you can know where you are in the titration curve, given a problem that says, hey, what's the pH after 5 mils of sodium hydroxide has been added? If you know the volume at the equivalence point is 15 mils, then you know we are somewhere in region 2. So we've added some hydroxide, but we're not to the equivalence point yet. Okay? So that helps you think about what type of problem you're going to be solving. So it's kind of a good idea to, when you're doing these types of problems, be mindful of where the equivalence point is. It may be a quick calculation that you want to do. And so I'm going to start with that. Okay? So let's say we have 15 milliliters of 0.2 molar HCl. We put that in a flask and dilute with 50 milliliters of water. Then we titrate with 0.0964 molar sodium hydroxide. I think this example ties in with a video I have on YouTube, so I'll link that on Carmen. Let's see. What volume does the equivalence point occur? So again, we know that at the equivalence point, by definition, the moles of OH minus added equals moles of H3O plus or H plus at the start. Okay? So if we know, and which we can know here, given our problem, we can know how many moles of H3O plus we started with. We have a volume and we have a concentration, so we can figure moles. And so we also have a concentration of hydroxide, so we can use that information to calculate volume needed of hydroxide to get to the equivalence point. To me, this is a dimensional analysis problem. I will show you another way of doing this problem, but probably on Friday. Okay? So let's do with dimensional analysis first. So we are starting with 0.2 moles per liter of HCl in a total volume of 65 milliliters. Okay? So we took 15 milliliters of that 0.2 molar, and we diluted that up to a total volume of 65 milliliters. Does everyone see that? Okay. So how will we find the concentration of hydroxide, or H plus, in that solution? What equation? Yeah, I think I heard it. M1V1 equals M2V2. Yep. Okay. So this is going to allow us to find concentration of H plus. I will say again, keep in mind here, we're using HCl. So for every 1 HCl we put in solution, we end up with 1 H plus. If this was H2SO4, for every 1 H2SO4 we have 2 H plus. Okay, so you got to watch that. Okay, so our original concentration of the HCl was 0.2 moles per liter. Original volume, V1, was 15 milliliters. Let's put that in liters, 0.015 liters. We want to find the new concentration. And, actually, I don't know that we have to do this, but we're going to anyways at this point. Total volume, 0.065 liters. Yeah, what am I doing? I'm so sorry. Well, here we go. We'll find this. We're going to need it at some point. got distracted thinking about the thing I'm going to show you on Friday. Okay, concentration is 0.0462 moles per liter. Okay. Oh yeah, no, we definitely need this. Okay, so we're going to have, we know the concentration of HCl in our flask. So we need to figure out moles, and then from there we need to figure out moles of OH minus that need to be added, and within that, how many milliliters of the concentration we have will be added to get to that many moles. That was confusing. So let's work through it. Okay, so we're going to have 0.0462 moles of H plus per liter of H plus solution. We have 65 milliliters of that, or 0.065 liters. So liters are going to cancel. Now we have moles of H plus. We know that because of our neutralization reaction, H plus plus OH minus forms H2O, that for every 1 mole of H plus, it reacts with 1 mole of OH minus, right? So this factor is coming from the stoichiometry of the neutralization. So when we cancel things out here, liters of H plus cancel, moles of H plus cancel. We now have moles of hydroxide, but we're asked to find the volume to get to the equivalence point. So here we can use the concentration, 0.0964 moles per liter of hydroxide that we're adding. Moles of OH minus now cancel, and we're left with volume of hydroxide. And I end up with 31.2 milliliters, well, 0.0312 liters. Okay. Questions on that? Yes.
In the beginning, do we have to convert it to the new concentration, or do we just find those?
Yeah. So this is where I confused myself, because you don't actually have to find this concentration here. You can start with the fact that we have, we'll do it again, 0.2 moles per liter of H plus. We have 15 milliliters of that, 1:1. And concentration of OH minus. Do we get the same answer? Yeah. Maybe we can round it, right? Why do we get the same answer both times? Does everyone know? Dilution doesn't change the amount of moles. That's a great way of saying that. So this is only dependent on moles. So someone asked last time or a couple lectures ago why we use moles in a reaction table and concentration in an ice table. Well, the reason we use moles in the reaction table is that we're reacting moles to moles. Concentration or volume doesn't change that. Does that make sense to everyone? So either way, you get the same answer, right? Questions on that? It's good? I'm going to go on, okay. Okay, so we know now that the equivalence point is going to occur when we've added 31.2 milliliters of sodium hydroxide solution. Let's go back now and look at calculating the pH at the various points along the titration curve. So the first one is, what's the pH before any base is added? What type of problem is that? A strong acid problem, right? So well, the only thing we need to know is concentration of H3O+. Okay, once we have concentration of H3O+, pH equals minus the log H3O+. And that's a relatively easy calculation to do. Now here we do need to be mindful of the dilution. Okay? So in the previous slide, we calculated that the H3O+ concentration was 0.0462 moles per liter. Okay, that's the 0.2 moles per liter HCl diluted up to 65 milliliters. So when you do minus the log of 0.0462, you get 1.33. Okay. Make sense? Okay, so then the next thing we need to do, we're going to part 2 of our titration curve, and determine the pH when 15 milliliters of sodium hydroxide have been added. Now, we know, because we've calculated the volume required to reach the equivalence point, that we haven't reached to the equivalence point when we've only added 15 milliliters of hydroxide. So, we need to do a reaction table. And we need to figure out how many moles of H plus are going to be left over after we've completely reacted with the hydroxide, and then determine the pH based on the excess. So for the last problem, we figured out the pH at the start was 1.33. How do you expect the pH to change after we add hydroxide? It's going to go up. Is it going to go up a lot? No, exactly. So we know our titration curve, relatively flat in this region, and that's where we are in terms of the titration curve. Okay? So let's attack this problem. So we are going to set up a reaction table or a BCA table. The important reaction that's taking place is the H3O plus OH minus forming 2H2O. Or H plus OH minus forming H2O. Either way, they're equivalent essentially. So again, in our reaction table, we need to use moles. Make sure you use moles. So for the moles of H3O plus, we have 0.0462 moles per liter, and we have 0.065 liters of that. And that ends up being 0.003003 moles. Okay. When we add 15 milliliters of 0.0964 molar sodium hydroxide, okay, multiply the volume by the concentration, and we end up with 0.001446 moles of hydroxide. If you're doing your calculation and you end up with more moles of hydroxide at this point, you know you've made a math error somewhere, okay, because we are before the equivalence point. So hydroxide is our limiting reagent. We have fewer moles of hydroxide. So we're going to subtract 0.001446 moles from both H3O plus and OH minus. Yeah, did I have a mistake?
Well, I'm just confused on where you got the .0462.
Oh, you can do this times this to get moles. But the 0.0462 was the moles per liter of HCl in total of 65 mils. What was the other, did you say you had a question about?
No, I said thank you.
Okay. Everyone else, everyone see that? If you do 0.2 times 0.015, you get 0.003, so it's the same calculation. Moles are moles. Okay, so we do our subtraction, and we end up with 0.001557 moles of H3O plus, 0 moles of OH minus. All right, we should end up with 0 there. And our pH, as we mentioned, is dependent on the concentration of H3O plus. So now we have moles of H3O plus, and we have a total volume of what? We started with our 65 milliliters of HCl. We've added now 15, so total in the flask is 80. And we should end up with a pH of 1.71. So our pH did increase, that's great. Didn't increase very much, that's logical. Okay? Questions? Okay. One more problem to do. What's the pH at the equivalence point? Well, actually, we have 2 more problems. So what's the pH at the equivalence point? 7. That's an easy one. That's why we love strong acid, strong base titrations. You can put as many zeros as you want. Okay. Assuming we're at 25 degrees C. Everyone okay with that? Okay. Okay, now we can do the other hard one. So here we are going to have added enough hydroxide, sodium hydroxide solution, that we are 10 milliliters past the equivalence point. Okay. We're going to do this 2 ways as well. Okay. Hang on a sec. Anyway, okay, I'll complain about that later to someone else. Okay, so pH 10 milliliters past the equivalence point. First thing is, we know the volume at the equivalence point, 31.2 milliliters. So effectively, this problem is saying, what is the pH when 41.2 milliliters of 0.0964 molar NaOH have been added? Okay. So again, we can set up a reaction table. So we're going to have our H3O plus OH minus completely reacting to form 2 water. Do our BCA. we still start with the same number of moles of H3O+. Okay? Don't worry about the fact that we did any other problems. We've already, or think about having reacted away some of that. We're just imagining what the pH is when we're reacting the starting moles of H3O+ with 41.2 milliliters of hydroxide. Okay? So moles of H3O+ is the 0.003003. Moles of hydroxide now is 0.0964 moles per liter times 0.0412 liters. And that is equivalent to 0.00397 moles. Okay, so what's the limiting reagent in this case? Go ahead, ask your question.
The question earlier where we calculated the 31.2 says the volume of base added.
Yes.
Oh, I see. We're only using it for the OH, not the overall solution.
Yes,
So it's
okay,
not the total volume.
good point, yes. So what is the pH 10 milliliters past the equivalence point? I guess this is sort of like the hidden question in here, the hidden implication is this is 10 milliliters of base added beyond the equivalence point. Okay, not total volume. Not total volume of the flask. Good question. Yeah, that total volume in the flask really only matters when we're figuring out concentrations of the species in the flask. It's kind of yeah, anyway, I don't need to get into that. Okay, so limiting reagent is the acid. So we're going to subtract 0.003003 from both H3O plus and OH minus. Completely reacted away that H3O plus, that's great. We know we're beyond the equivalence point. We shouldn't have any of that left over. And the excess hydroxide is, we'll have 0.000969 moles of hydroxide in excess. And so we mentioned last time, or when we were looking at our titration curve, that the pH past the equivalence point is only dependent on the moles of excess hydroxide. So we need a concentration of hydroxide, and then we can find POH and then pH, okay, using that conversion again. So we have our 0.000969 moles. And the total volume now is 0.065 plus 0.0412. Total volume of 0.1062 liters. Okay. So our hydroxide concentration is 0.00912. Everyone okay with that? So we can calculate POH equals minus the log of 0.00912. We'll get 2.04. So pH is 14 minus that, 11.96. Which is great. We've got a base, right? We should be very basic at this point. Questions on that? You want to see the other way to calculate this? Slightly easier. It's slightly easier. Okay. So the other way of doing this is recognizing simply what the problem says is that we're 10 milliliters past the equivalence point. Okay. So we have 10 milliliters excess hydroxide that have not reacted with the acid, all right? So if you think about that, we've added 41.3 milliliters of base. 31.2 of those have reacted with the acid. There's no acid left over. 10 mils are unreacted, okay? But we don't care about that. We want to know moles. So, and then to get total volume. So the moles of hydroxide that are left over after reaction, so you're essentially doing a BCA table, but having done the subtraction first. Moles left are concentration of base, 0.0964 moles per liter. We know we have 0.01 or 10 milliliters excess. So we end up with 0.000964 moles of hydroxide, which is essentially, which is essentially this value. There's rounding errors. Okay, so we get the same number of moles. You see that? Okay, so we want concentration, 0.000964. Total volume's the same, divided by 0.1062. Same problem now, we got 0.00907. POH equals minus the log, 0.00907. And that still ends up being 2.04, and so the pH is the same, 11.96. So there's two methods here. Pick your favorite. Questions? Yeah.
How did you get that
The 0.1062 here, this is coming from this is the total volume in the flask. So it's going to be the 0.065 of acid that we start with, and we're adding 41.2 or 0.0412 liters of base. So if you do the 10 mils past the equivalence point, you have to know the total volume of that. Yeah. Okay. It's fun, right? You can tell that this is really what you want to be doing right now. Okay. Questions? All right. We're going to do a little intro to weak acid plus strong base. We won't do any more problems today. Okay, so titration of a weak acid. Oh, I guess I should say this. You can expect to see problems where with strong acid plus strong base, where you start with the strong base in the flask and you add strong acid to it. Those are done the same way. You just start out with a basic pH and you end up with an acidic pH. Okay? So those are fair game as well. I'm not going to do any specific problems on those, but they follow the same trends. Okay, BCA tables and things like that. Okay, so titration of a weak acid with a strong base. This is, again, why it's really important to recognize what the weak acids are, because we do these problems differently. There are 4 regions, again, of the titration curve. We'll talk about each of those, but take a look here at the difference in shape of a strong acid curve, that's the dotted line or dashed line, versus that of a weak acid. So the titration curve for a weak acid, it has a much more gentle slope, increasing slope when it's a weak acid titrated with strong base in region 2, as opposed to mostly flat and then sharp increase with strong acid. So you see a much more gradual increase here. That's something you should be able to recognize when you're looking at a titration curve. Okay. The other thing to note is that the pH starts off higher for the weak acid compared to the strong base. Why is that? Because it's a weak acid. That's the answer. But what else is something that you notice? So equivalence point, remember, is the volume. Look at that. The volume required to reach the equivalence point, if you start with 0.1 molar of weak acid and titrate with strong base, or 0.1 molar of strong acid and titrate with base, the volume required is the same. Why is that? Because the neutralization reaction is the same. Okay? I think I have basically that question on the next slide. Okay, so difference is starting pH is higher for a weak acid titrated with a strong base. The other thing is that the equivalence point pH is greater than 7 for a weak acid titrated with a strong base. So it's not 7. The pH is not 7 at the equivalence point for a weak acid. Why is that? Brayden.
Since the weak acid has a weak base conjugate, it would be the Henderson-Hasselbalch equation, and when so it should be pK, right?
You're on the right track. So when we react our weak acid with the strong base, completely reacts at the equivalence point. We've added stoichiometric equivalence. We end up with A- plus water in solution. Okay? But what do we know about A-, our conjugate base? It's basic. Exactly. And it has equilibrium with water. Right? So this equilibrium, the conjugate base plus water in equilibrium with HA plus OH-, is the reason why the pH is greater than 7 at the equivalence point. Volume required to get there is the same as if it were strong acid, but the pH is different. Okay. So why is the volume the same? Both react 1-to-1 with the base. So same amounts needed. Okay. Questions on that? Should we stop here? It has been decided. How's it going?
Hey, Professor, I don't actually know where you got it. Well, I know for like a 2
Sure, yeah.
Where did this come
So that was from, one of the first things we did for this problem was calculating the volume required to reach the equivalence point. Yeah, there might be around.
Okay.
That's totally fine.
Oh, so that's all it is.
That's all it is, yep.
Thank you.
I might not. No, that's sort of, it's neutral is defined as having equal amounts of H plus. But the pH doesn't have to be set. Did that help you? Wait. Actually, one more, because I think
Because like on CLab we have, I know we're doing what this is.
Okay.
For one of the equations, it had like the coefficients when you did the like balance equation. Does that affect the amount of moles that are in? It does.
yes, it affects the number of moles. So is it like a,
So it's like basically like if you're like this would technically be minus 2x.
if you have two hydroxides?
Yeah. If that was like the original code.
Oh, yeah, okay. Yeah, so actually this reaction stays the same. But the number of moles that you start with, so for instance at H2SO4, they give you a concentration of H2SO4 and you want to find moles of H plus, you have to multiply that by 2 because there's 2 for every 1.
Okay.
Same would be true if you had calcium hydroxide. When we give you a 0.1 molar calcium hydroxide, you have 0.2 molar H minus, and that's it.
Okay.
So this reaction stays the same, but what you start with will change.
What is okay. Thank you.
Hello.
Just wanted to ask, so with the weak acid strong base titration, so the reason that the equivalence point is higher is because of the conjugate phase?
It is present in solution.
So what does the equilibrium mean, like in terms of?
Yeah, so it's showing that with this in solution, you are forming hydroxide, so that's why you have this pH.
Oh, okay. Okay, that makes sense. And then I wanted to ask, so if you do like a weak base and strong acid titration, it would just be like flipped?
It would be flipped,
Be
and the
flipped.
pH at the equivalence point would be less than 7.
Okay, thank you.
How's it going?
Good, how are you?
Good.
Lab's still a bit behind, because we're going to be caught up with the weak acid and base titration, but I noticed that for yesterday's lab, we had no idea what we were doing.
Yeah. We do not have a good mechanism for matching all of this timing up, unfortunately. So you got to do your titration yesterday.
One thing I think my 12th 10 professor did after a while was kind of just make like a brief slideshow outlining what equation we'd use and kind of like an example problem or two about what we would be behind on in lecture that we'll be doing.
I see.
So I think something like that might help, because I tried using the internet and they had a much different way of doing it than we did in the lab, which was wrong, so.
Oh, no.
Yeah.
Yeah, okay. Okay.
Just want to let you know about that, because
Cool.
a lot of people in lab are like,
Frustrated, I'm sure.
yeah.
Yeah. It's something that is on the radar of people who teach and people who do labs, so hopefully we can keep working at it to make this.
Review on Monday, so that kind of bit.
Yeah, the other problem too is that the other sections of 1220 are Tuesday, Thursday, and they have more class time ahead of what we have, so they're probably a little bit ahead of us as well. I'm sorry.
No, you're good. I just wanted to let you know, there
Cool.
might be a solution, but it's just,
Yeah, it's unfortunate that you don't get enough material within the lab itself to.
well, we do know what we're doing. I mean, TA, it depends on the lab section. Some TAs will fill you in really well.
I
Other
see.
TAs will just fill this in really well, so
Okay.
they basically taught us everything we need to know in the class.
Hey, great. Yeah. I mean, it's good to see it twice. Yeah.